Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm Catherine McKinley. It's my pleasure to introduce Xiaoyang, who's been working with for 2 years while he's a PhD or master's student at ANU, working with Professor Steve Blackburn, my colleague, who I've collaborated with for a long time. And so he's just switched last month to be a PhD student. But before he was even a PhD student, he's produced 2 pieces of really interesting work, and we get to hear about one of them today.
Yeah. So, and you already got this nature. So, and it's interesting. So, my mom sometimes asks me a question. So, what you said you are doing some research, and what are you doing? I said, garbage collection. and my mom get quite unhappy. It's garbage collection. And you said you do computer science. So I'm going to in the talk. I show this slide to my mom. I said, this is nature, and he do something has some same word with me, but also different. So yeah. So yeah, nature talk about a lot of nothingness, and today we're going to talk about why nothing matters, right? But there's no philosopher here. So I'm Xiang. So this is a co-work with Steve, Daniel, Jane, and Catherine. So yeah. So and zero-initialization. So one of the problem of old systems like a embedded operating system and native languages, they have a common problem, which is, for example, you say whether a global value is initialized or not. It depends on your system. There's no specification about that. So I'm a maintainer of a small operating system which is used in the satellite and basically embedded system. One day ask a question, say whether your system is 0, the BSS section or not. And the maintainer answer this question kind of like, your answer, it depends on runtime version and the BSP, and there's no rules about that. You should take care about it yourself. Otherwise, your satellite crash doesn't matter with me. So, and so satellite crash is not a good thing. So, and new languages, they don't have this problem because in Java, they have specification called every variable in a program must have a value before it is used. And it's not only for Java, most of modern languages, they have this specification, and the idea is try to avoid this problem. So, and your application programmers don't need to think about that. They naturally know that all of the value is initialized. For the local variable, the compiler can check. The local variable is initialized, assigned first, and you start to use. But for the non-local variable, this work is typically performed by the garbage collector, which zero-initialized all of the global variables. So, and for example, you get application, you get application said, please give me array, and your garbage collector is coming, and your garbage collector said, and then before you deliver this array to the applications, you have to zero this array for application programmer to get clean data. This we call zero-initialization. Simple, and yeah. So does this matters? And people in the common sense is kind of like, this should not be hard. This should not be quite high overhead. And the people, it's hard to notice that. Their story is kind of like, I give this talk in Uppsala last week. And after the talk, a guy came to me, a guy who is doing the hash algorithm for their commercial systems. And he said that he has a similar problem with his paper mentioned. And he designed a fancy hash algorithm. And he started to optimize this algorithm. But he found that it does not matter which kind of algorithm he chooses, the system performance is really bad. And because he's not a computer architecture guy, he asked another friend who plugged in the performance counter and found that half of their CPU circles spending on zeroing the bucket. So, yeah. And this tiny problem is just not easily, be mentioned by a programmer. So this way, we measure the CPU, the percentage of CPU circles spending on zeroing across about 19 Java benchmarks. And you have seen that one benchmark is weird. It's kind of like spend about 50% of CPU circles.
Is that percentage or fraction?
It's
So is that 0.6%?
it's a 50. No, it's a 50%.
So it's fraction.
Yeah, it's a fraction. Sorry. Yeah. So the half of the CPU circles do nothing, just do the yeah.
Is this in Jakes or hotspot?
Jakes.
Jakes.
And also, we validate it's in the host mode is also true, because it's the nature of the program. It's not a JVM. So
But is this in the same? It's when I request memory,
Yeah.
it gets zeroed in the same thread, or is it in some other thread that is actually doing the zero? Can it be hidden by?
I will talk about that later.
Okay, great.
Yeah.
When you say cycles in a multi-core system,
Yeah, we measure the total. Yeah, good question. So we measure. This does not represent the percentage of execution time. This is a percentage of workload you do. This is we measure how many CPU circles. For example, in two CPU, each of them spend half of them for zeroing, and totally you get 0.5% of CPU circles you do zeroing. So yeah, and this is interesting, and we dig this problem, and this problem comes from a bug, because the search is a benchmark which uses lucens to search something, and the lucens is quite popular in search area, and that bug resides in lucens for 1 year, and the reason of the bug is kind of like when you try to pass a string to a token. And they get quite complex system to handle this. And one guy is coming to the system, say, I'm trying to optimize passing the string to token. And he refactor the whole stuff. But he forget, in the deep side of the system, there is a object there is a function, there's a class who allocated a large array every time you create this object. And he forget that, because it's really deep. And he didn't understand the whole system, and he started refactoring. So, and there's bug coming. And they have a lot of problems, and they try to find it. They know the bug, but they didn't find it until 1 year later. So, and we fixed that. We use a new version. We fixed that bug, and it's come down to 8%. So, but still high. So on average, you got 4% of CPU circles on zeroing, but some benchmark to get 12%. So this number, yeah.
If you spend that much money, why put something as boring as zero? You could put a number that can trigger an exception as soon as you see it in a register, and then you will do some useful work. But probably the language lawyer will stop you.
Sorry.
yes.
But
We had one.
in a project ages ago, we put 5555 in memory, and any time that cropped up in a 16-bit register, we stopped the simulation. And it's found lots of interesting bugs.
Oh yeah, sure. So
You can't do it with zero.
We did that for null pointer exceptions. And we stole bits so that you could trace back the source of where that null pointer came from.
Yeah.
So that's a very useful idea. We
Well,
wrote a whole paper just about that idea.
That's Kahan's acquired NAND. which
Right,
also
right.
Go
But-
propagate and tell you where they come from.
That's right.
right. Yeah.
And in Java, because you're 4 byte aligned, you can steal bits, so you know that it's not some other value.
Yeah.
Yeah. So and how does it work? So they mentioned. So currently there are two approaches. So in the first slides we have seen that the key point is that your garbage collector has to deliver the clean data to applications, and you can do anywhere before you deliver the data. So the one is that you bulk zeroing them. So the idea is kind of like you are going to zero quite early, but you're going to zero a large block, right? And so if you get a whole block and full of garbage. So, and you can zero the whole block once a time. And then you create the object inside this block. And this happened when this in JIX-REM, this happened when one thread, so the allocation of on nursery, there are two steps. One is allocate the big block, and another one is allocate the small object inside block. This zeroing happens when you allocate the block, and So, and another is hot pass. The idea is that you delay the zeroing as late as possible. So, and you have a block of garbage, and you don't zero the whole block once a time. You create the object, you just zero the object size. You just zero what you need. So, and you zero another one, and you zero another one. So, and this is two common designs in all production systems, and it looks like the people prefer hotspot zeroing, hot path zeroing, because a lot of production JVMs use hot path zeroing, and one day I talked with a guy who working in Azure about my idea, and he thinks my idea is really bad, and people assume that hot path zeroing is the best approach to handle zeroing. So, and because for the bulk zeroing, because you zero the whole block once at a time, you get a sequential reference the whole block, so you definitely get good spatial locality. And but the problem is that you zero a whole block, there's a long distance between you zeroing and the first time you reference the object you created on it. So, and for the bulk zeroing, because the block is large enough, and you are allowed to use a function such as a memory set function to zero it. So the instruction footprint is pretty low. For the hot path zeroing, because the nursery space is sequential, and your Java program is likely to allocate a large number of small objects quite fast, because language encourage you to do that. And so it still has a good spatial locality. And it has short reuse distance because you just zero what you need and start to consume the object you zero. And but the allocation code normally is inland to the normal programs, and zero instructions inside allocation. The zero instructions these zero instructions inland and everywhere to get a larger instruction footprint. Another one is kind of like that, because every time you zero, for example, for the left side, you zero a 32 kilo block, and you don't have many control instructions inside the block. You can use your hand to write the assembly language to control that. But for right side, it's generated by compiler, and every time it's just a zero, a quite small block. For each block, you get some control instructions overhead there. So, okay, so what happened? So let's say this is one of the guy who got a Nobel Prize in our uni. So, and he got a cool tools, kind of like a microscope use, right? And we don't have, computer science don't have cool tools. Right, but we have macro benchmarks. So right, we use macro benchmark to enlarge the effect of zeroing, and this is a stupid benchmark. And this benchmark basically allocate many objects as he can and consume this object again. So, but this is perfect here because the zeroing is really important here. And in some case, in some situation, to reflect the real Java workload, which is you allocate a large sequential small object and use it and throw it away. So, and we analyze this micro benchmark on top of Intel Core 2. Some guy asked why you choose such old machine. The idea is kind of like you have a front side bus, and which give you a chance to break down all of the transactions. You should understand the problem deeply. We got the general efficiency, 32 megabytes nursery, 32 KB allocation block. So for the bulk zeroing, it allocates a 32 kilo block and zero the block once at a time and start to allocate object inside the block. For the hot pass, it gets 32 kilo block, do not touch it, and allocate one first object, zero it, allocate another one, zero it. So until you get the next 32 kiloblock. This is for nursery allocation. And it's interesting. There is actually in the hotspot JVM, they do have in G1 they do have they call garbage first collector, and they do have a concurrent zeroing. And I asked some guys probably who related with that garbage collector. I said, could we concurrent zero in the nursery? And he said, that's a bad idea. Don't do that.
I have a question. In the hotpath zeroing, do you inline the zeroing into the application code?
Into the allocation. And the zero instruction is basically in the hot path allocation code. And the hot path allocation code is inland to
The application?
applications who need to do the allocation.
So
Based on the JIT policy.
Sure,
Yeah.
sure. But if it is that situation, is there the possibility that in this code that your standard compiler can dead code eliminate the zeroing? Because you know that you're guaranteed to write before you read, for instance.
You mean it's guaranteed to write before you read. But in this
so
code,
you're writing to fresh sub j before you actually read from that particular location. I was just curious if the compiler is smart enough, if the JIT is smart enough to remove the zeroing code that would happen temporally before this.
Yeah, we make sure that and there another optimization here. You just do a escape analyze and delete the whole code. You can also do that, but we try to make the variables static, and we try to check the generated code by both by JXRVM and hotspot JVM to make sure they do what we want. And for JXRVM, we use a replay to control the JIT. So what we check the code is what it generated.
But hotspot had that optimization in there,
That was what I was getting
but
at.
it slows down the program.
And hotspot has a optimization, which the idea is not this one. The idea is if you know for example, when you allocate the array, and then you initialize, but not by the program. It's initialized constants. You have an array which is equal and something, and the hotspot will try to analyze the programs and try to pick up something you write there and avoid zero them, and which does not work. And this is quite interesting. So sometimes you think that it works. Sometimes you think it avoids the number of write instructions. But the point that in modern architectures, the number of instructions to write is not that important. The most important is data locality stuff. So, yeah, and so all of the optimizations, I think it should based on the quantity analyzed first, not a optimization first. And yeah, and it's yeah. So, and which one is better? So at first we try to look at the number of returned instructions, and we found that the hotspot is returned about 20% more instructions, and which is what we expected because it's inland such more code. But it's interesting that this bar represent the total bar represent the execution time, and the right bar represent the percentage of CPU circles on zeroing for bulk zeroing. But for hot paths, because it's inland, we cannot easily measure the CPU spent on zeroing. So we make this light blue. Right, that's the idea. So we found that the hot paths, they got 20 more instructions and run 15% faster. That's the optimize they do is that you remove the number of instructions, not that quite important in powerful machines. So, and we try to understand this problem and why. And the first time is definitely something about the memory subsystem. And we measure the number of bus transactions. And this number is hot. All of data is normalized to the bulk. So both of them generate same number of bus transactions. It does not answer us other question. So, and here's the write transactions, still same. The fetch transactions, write transactions, still same. So, and still does not answer our question. So, and here it is. And the most important is, and you get a fetch due to program. For the bulk, a lot of fetch transactions due to your program missed cache, and you start to fetch. But for the hot path, most of the fetch transactions actually are generated by prefetcher. Hardware has a automatically prefetcher, and it detects your memory reference. If it is sequential, it's really simple. It's some patterns, some simple patterns. If it's sequential, that's the first requirement. Another one is if there's some free memory bandwidth, and the prefetcher start to work. And so this tells us that hot paths really take advantage of prefetcher. Why? Why take the advantage? This is quite simple. So if you get bulk and you zero the whole block quite sequentially and fast, and your instructions whole of the instruction is pushed to the memory subsystem, and your prefetcher cannot catch it up, and there is also no free resource. The prefetcher just does not work in these situations. But for the hot path, when first time you allocate object and you start to consume this object, and start another one, start consume it. But the key point is that the nursery space is sequential, and because you sequential allocate on a sequential address block, actually this block shapes your application's behavior, make your allocation sequential, and the prefetcher can catch it up. And you create an object, and you start to consume this object a little bit, which gives a prefetcher a time to prefetch the next one. So that's why and for example, this object is already in cache, so fast. So what happens when we disable the prefetcher? That's a question. So, and what do we have to say that the hot path takes the advantage of prefetcher, but bulk does not. What happens when we disable them? We are lucky on the core 2. There are 2 registers. You can disable 2 kinds of prefetcher. In the core 2, there are 2 policies. One policy is that if you miss and you fetch the next line beside the miss address. Another one is detect the sequential of your applications. We disable both of them. So all of the data is normalized to bulk. We can see that when we disable the prefetcher, the bulk performance does not affected anymore, because it does not need the help from prefetcher. It's already pushed instruction to the memory subsystem. But if we look at the hot path, it used to get a 15% speed up, but now it's got 10% slow. So yeah, this answers the question. So the most important that on current modern architecture, the prefetchers help those references that are sequential, but you cannot that fast. And there's a tense here, and you make it complicated. The hot path, you make it like the hot path and the optimization you mentioned make the whole program quite complicated, and actually it's not fast sometimes. So how can we make it simple and fly faster? This idea. So, and the answer is it's really easy. We just replace the write instruction, the store instruction, with the non-temporal instructions. What is non-temporal instruction? So on the normal temporal instructions for the write-back cache, you basically, because when the guy who designed the CPU, there are really 2 principles. They learn from the application. One is that you got a temporal locality, and another you got spatial locality. So for the write-back cache, if you get really good temporal locality, that's perfect. You fetch it for your write, you fetch the cache, and you consume it forever and never write it back. And but sometimes you have to write it back because the cache is small. And here's the normal store instructions. And here's the non-temporal instruction. Non-temporal instructions is designed actually for device like GPU. So for example, you want to generate the image, you have to write the image to memory buffer. And the write to that image, the order is not important because the human cannot distinguish the orders you write pixel. And another one, the device is in other side of the bus. You want to dump all of data to the memory first. So that's why you get a non-temporal instruction. You directly write down to the memory without read it first. So the idea is you can get a double throughput because you take advantage of all of the memory bandwidth and you bypass the cache. But the drawback of non-temporal instruction, there are two drawbacks. One is the non-temporal instruction really have weakly order compared with normal stores. So you cannot use it fine-grained. You must zero a big block. Another one is because when you write the data, because it bypasses the cache, it's directly to the memory. But if you want to consume it immediately, you have to fetch it again to the cache again and pay the penalty. Right? So that's what is non-temporal instruction. If you do not need to pay the penalty and the non-temporal instruction is perfect for you, what we learned from the previous result is kind of like the hot pass actually is missed in the cache, but it runs faster because your prefetcher takes advantage of that. Because the prefetcher identify your sequential and prefetch the data to cache first. So it's okay, the prefetcher will help us. So we can safely use non-temporal instructions to write a block, to zero a block. And later, when we start to consume this object, the prefetcher help us. What's the result? Here it is. So the right bar still represent the CPU circle spending on zeroing. And the non-temporal bug is quite simple. We just replace the memory site with a hand write a sample language write a function. It's called memory nt something. So we can see that it gets double throughput. So the white bars get. Yeah.
Are you doing SIMD writes, or are you doing single?
Sorry.
How are you using? I mean, there's non-temporal writes using SIMD.
Yeah, with this basically use this each time you write about 16 bytes together. So with a MMX registers. So yeah, and the interesting part here is that the blue, if you compare this bug and the non-temporal bug, the blue bar actually does not grow. It grew a little bit. It does not. I mean, people assume that. I talked with Azure guy, and he worry about this part. He thinks this group bar will group up somewhere else. So, cause he think when you reference, you still have to fetch there, you still pay the penalty. But he forget the prefetcher actually can help us. And that's also one of the advantage if you compare with Java to some old C systems which use freelist malloc. So
we actually tried to use the wider instructions, but because they weren't aligned, that
they have to be, right?
That you have to do this on aligned.
But if you're doing bulk loads, can't you just
for the bulk you can use anything.
Do the regular part for the unaligned part, and then deal with the aligned part. Hopefully that's the one. Start with the first aligned byte.
That's right. Yeah. That's right.
For the hot pass, that's another limitation. Hot pass zeroing. You are not that. You cannot.
You're in random parts of memory.
That's right.
Yeah. So, and but sometimes you see the right bar, the white bar is still pretty. It takes for the real workload. It still takes about 4% or 3% CPU circles to do the zeroing. So the idea is that because we directly write to memory, we get an advantage, which is another advantage of non-temporal bug zeroing is kind of like because you bypass the cache. For the CMP multi-core systems, you avoid the cache pollution, so you can safely to do a non-concurrent zeroing. But with normal store instructions, if you do the concurrent, zero a big memory and you flush all of data in the cache. So and sometimes when one core is sleeping, and we give him a job to zeroing the block for the consumers. So, and we call it concurrent zeroing, which is very simple. The idea is at the end of GC, your zeroing thread start and zero the map. This is another advantage of Java. About garbage collection. Say you can set the nursery space as a fixed size sequential block, and your concurrent zeroing thread just directly zero those block. You don't need care about any other things. So concurrent zeroing. So yes. So and it gets faster. So and it's better than all of them. And so let's see what the zeroing. So you can see that we offload that zeroing to another core. Also, it consume it consume more CPU circles for zeroing, but it's okay because in another core. Yeah, because you have contentions on the memory system, you can get longer time to zeroing. So, and yeah, astronomers get telescope, and this is also try to answer my my mom's question. Sometimes I also do some sense. I'm not just recycle the rubbish. So yeah, so we have to look to real workload. We don't have telescope, but we have real workload, this is across 19 Java benchmarks, which mix some from Da Capo and some from JVM. And this is current two designs, which is bulk with non-temporal. Bulk with hot path zeroing. And this data is normalized to bulk zeroing. So we can see that sometimes the hot path zeroing get pretty good, and sometimes it get worse. So overall speaking, it's just roughly same in our systems. And the key point is that for hot path zeroing, you make your system complicated, and you limited the choice, you limited the optimization you can do, and your JIT compiler get complicated. So and sometimes, and this is interesting, if you look at the current hotspot source code, and they do have a bulk zeroing, but it's really it's implemented with it does not use memory set. It just has some writing in C and pretty slow, and it has a comment there that this bulk zeroing is used for debug. So which means they got hot path zeroing, and sometimes the problem about zeroing, they switch to bulk and check whether this is a zeroing problem. And yeah, so. And this is our non-temporal bulk and the concurrent result. So, and you can see that for some benchmark which consume a lot of CPU circles on zeroing, our non-temporal bulk zeroing first get faster because you reduce the cost of zeroing, and the concurrent zeroing get more faster because you offload the zeroing to another core. But the problem is that when there's no idle cores, and all of the threads are busy, are eager to consume the zeroed memory, and your concurrent zeroing get worse. So, yeah, I mean for optimizations, it's really important. So you should not slow down some guys, and right. Yeah.
Yeah. We're trying here.
Yeah. So we try to make a adaptive zeroing, which is quite simple. At the end of GC, we switch between them based on some simple environment, like we check the number of application threads and compare with the number of cores we have, and make a decision between the concurrent and the bulk. And then here's the open question here. See, so JVM sometimes you can actually do the scheduling thread. Your JVM actually sometimes can do better than the operating system because you understand the semantic of your applications, semantic of your threads. But due to current system design, it's not that easy to control by JVM. And so and your JVM does not understand the whole system workload. So that's why we choose this quite simple decision, and it works quite well. Well, but if you are a busy system and concurrent running with other workload, maybe it does not work as good as this. So we always choose the best, or which we among them, or we don't slow down the system. That's a very important part. So, and yeah, so we found that the zeroing matters and take significant CPU circles on zeroing. And current design, we try to deeply understand the current design. We run a lot of experiments to find out the reasons and break down the bus transaction to help us to understand how does the hardware and software co-work together. And based on our understanding, and we propose two designs, and very simple. and very easy to implement it. So it probably take about, to identify and analyze this problem is hard. But after you know the reason, and probably a JVM developer take about 1 hour to finish the coding. So yeah, and we got a implementation which gets 3.2 average speed up. So sometimes 3.2 is a small number, but you just need 1 hour and 3.2, which is, and the most important for hotspot is they got thousands of lines code to do the optimization you mentioned, and you can delete them. And
not if you're the developer that wrote those 1,000 lines of code.
yeah, and it's a huge function to, because you have to analyze the bad code, and a lot of corner cases you can make sure, because you avoid zeroing something, and you make sure you avoid zeroing something is safe, and that's why they have a bug zeroing, which for debugging, and yeah. So I dropped the paper to the mailing list, and they said they are interested, but I don't know whether they have time to do that. Just a coffee time, finish that. So, yeah, and we are going to the next version of GXRVM will have our version, but for hotspot it would be good for them to finish. Yeah, that's it. And the nature to show that I'm doing some sense.
Somehow you didn't make clear that you did most of it in hotspot also.
Right, I did some.
Got similar results.
Yeah, and because I have to check the hotspot source code and say whether they do some fancy smart things. But it looks like that they don't do the experiment first and they directly write code. Yeah.
So how would this change if you had an architectural instruction that let you basically zero a cache line without having to ever prefetch?
Interesting. Yeah, exactly. So some architecture like PPC, they have a special instruction called DZBZ, and the instruction will directly zero a block without fetching the data. It directly zeroing cache. But the problem is that the DZBZ, I talked with IBM guys, and they don't like to use that instruction. So the reason is that as we mentioned, the prefetcher actually already prefetched the data in cache for you. But if you use DZBZ, the prefetcher cannot see your operations because you don't touch any memory actually. So you just zero the cache. And that's why they don't use DZBZ. Because, for example, if you write a large block of memory, if you use DZBZ, actually it's slower than fetch data from memory to cache. But you avoid.
Instruction was implemented poorly, or is that fundamental to?
It's okay. One reason is that it's implemented poorly. Okay. Another one is, for some cases, people ignore prefetcher. The hardware prefetcher. The hardware prefetcher sometimes can help you. So if you use DZBZ, it affects the prefetcher. The prefetcher cannot identify the patterns. And Azure, they do have a special better instruction which make the DZBZ kind of like a prefetch instruction. But the point is that you still cannot, it's still zero, right? It's still executing instructions. You still do not, if you concurrent zeroing, you offload all of the things to other cores. If you zero in the hot pass and you get you still pay the penalty. But when you try to do the concurrent zeroing, and you cannot use these instructions because you cannot bring them to cache. If you bring them to cache, you got to flush the cache, which you pay penalty. So here's
So to do DZB zeroing, you have to do it in the hot path to make it worthwhile.
Yeah. Otherwise, you flush the cache. You don't want to. For example, I run a program and another thread is coming, just reference a block and flush all of this program data out of cache. And when I was working and I had to fetch.
Depends how large a block you're zeroing, but okay.
Well, but the point is
that with the bulk zeroing, you have to do it that way. But the trick is on the allocation sequence is that if you're doing it in the hot path, you have to bring it right before you want it, right? And you have to do a cache line aligned, and so you have to do math essentially to figure out where the last object is and if you need to go get the next cache line. So it's basically introducing a lot of junk that didn't have to be cache line aware into your hot path allocation. Hot path allocation just said, put zeros here if they're aligned, unaligned on the cache line or whatever, I don't care.
And
okay? And when you use DCB0, it has to be cache line aligned, so you basically have to do math to figure out where you are on the cache line if you need to go zero the next one.
And for the concurrent zeroing, for example, the nursery space is, we use a quite small nursery space. Actually, it's a 4 times of number of last level cache, which is a 32 megabytes. But if you look hotspot, they use about 100 megabytes nursery space and which means one thread is going to 100 megabyte memory, and another thread is working. So if you bring 100 megabyte data to cache, and you can imagine what happened in cache. So.
But I think that the architecture that does the fetch on the right, even in Norm Jupe's paper, like 20 years ago, he shows that you shouldn't fetch the data, that you should have per byte valid bits, right? And so then you get around both problems. But nobody's got that.
If I get it right, you initialize to 0, so any reference to uninitialized data will trap to the debugger later.
Right.
Now that trap is not quite as urgent as straight code. Can you use essentially do something clever? So detecting the uninitialized read comes later, just early enough to stop the deployment of the airbag or the ICBM. And
well, the key thing that if theoretically you can, but the point is that how can you make it simple and it works, right? So and current, well, it would be, but it would be good. We can avoid all of the. You can analyze bad code ahead and see what happened there, but yeah.
We shouldn't be moving all these zeros back and forth to memory. I agree that we shouldn't be moving all these zeros back and forth to memory.
Mm-hmm. But this,
smarter architecture.
Yeah, if you are free and you design if you can image architecture, and you can get away all of these problems. But the point that the reality is not like that. x86 is a majority. And we should make a trade-off between simple and for x86 actually this solution is simple and effective. So if you can make a complex thing super fast, and I think it's worse. But the point that we don't have, you understand. I think you understand. Yeah.
So the problem that you talked about is application specific, right? I mean, it's at the level. It comes about because all of the semantics of the language say that when I get a piece of data, it's guaranteed to be 0. Yeah. So that is to say that. That's the language specification. It's the language specification. So it's going to happen whether or not I'm on x86 or not, right? It's not an architectural problem.
It's not.
So I'm curious about. So the problem exists on other architectures, for instance, phones. And I'm curious whether or not you think the solutions are going to be architecture specific.
I think this is an architecture problem too, because when people design the architecture, they have to provide service for applications. They are not architecture. It doesn't matter. I mean, if the user is happy and your system is good, if a user does not happy, it does not matter whether your architecture is fancy or not. Do you agree with that?
I guess my question was
this problem.
What's the solution for ARM? Right? Is it the same solution, or can we use non-temporal loads or stores for ARM, and that will solve it?
ARM has some other interesting instructions you can play with. So, but I don't think they have non-temporal. I will check later. But I remember it does not have. I check with. Do
they have the fetch no allocate? That will work too.
PPC has fetch without write. Zero. No, there's no write without fetch. There's 0 without fetch, and ARM has some interesting instructions for the array boundary check and some faster exceptions. But it looks like they don't have non-temporal instruction. I will check that. I'm not sure. I'm not 100% sure.
So another way to say this is what Catherine was saying earlier, is that if your results are to believe, if they hold on a different architecture, then a large amount of power is being consumed by our phones by just zeroing memory. Right?
Sure.
Yes.
Just zero.
Which is ridiculous.
Following up on that, did you have any tests or results about the relative energy efficiency of the various types?
We tried that. As we show that, we have a slide which show we disable prefetcher and enable this prefetcher, and we built the current sensor on x86 to measure the power of the chip, CPU chip, and we disable the prefetcher. We enable the prefetcher on core 2Q, and we measure the energy. There's no difference, right? So there's two answers for this question. One is we don't understand how does it do. You can disable prefetcher, but that part of logic probably not power off. And another one is that another one is interesting, which is maybe a lot of power is not drawn by the CPU, it's drawn by the dynamic memory part because you reference a lot. And for core 2Q, there's a problem which is memory controller is not inside the CPU. Memory controller, they call it NOS bridge chip. Memory controller is in NOS bridge chip. And our tools, because it's very simple, we cannot measure the NOS bridge chip power consumptions. So that's we think there are some effect, but we didn't prove it. So yeah.
So in the future, hope this design should be better with energy, but right now it's hard to tell because there's essentially the idle energy and turning off the things doesn't show up when we measure it very well because the chip doesn't have power control. Power to the different features isn't selectively turned down or up.
Yeah.
It's all you run at one voltage, everything runs at that voltage. And so the voltage domains don't let you do fine-grained things like you turn off the prefetcher and you get a big energy savings from that. You don't see that.
But Intel is going to provide some tools in the new and Sandy Bridge machine. You can get 3 sensors. One is measure the whole package power, and one for measure the core power. There's 4 sensors. Another one measure the anchor part, and the special one measure the memory part of the power consumption. But that machine is not. They plan to release that machine this year, but that is going to be maybe next year. So we need more tools to modify the energy effect. So yeah.
Right. Let's thank our speaker.